Hi y'all, this is Mel. Welcome back to Heat and Mass Transfer. Today we're going to be going over problem 8.009 from the textbook. So with this one, we've got an oil pipeline. We love our fossil fuels in this house. Um, that was a joke. We've got a pipeline that's 100 kilometers long. Not that long, but it's pretty long actually for our general like purposes. Because normally we look at things that are pretty tiny, but like yeah, 100 kilometers. Um, We've got our diameter, 1.2 meters here, and we've got our oil flow rate, m dot, 500 kilograms per second. We are also given the properties of oil as rho is 900 kilograms per meter cubed. Cp is 2,000 joules, kilojoules I checked, per kilogram Kelvin. And mu, which is our viscosity, of 0.765 newton seconds per meter squared. And we're asked to find the pressure drop, the flow work, and the temperature rise caused by said flow work. We're going to make a few assumptions. Quality of life, steady state and incompressible. Um, the flow is fully developed. We're going to assume that because it's a really long pipeline, so I don't think we're going to have any entrance length problems. Um, no velocity or elevation changes. This is just getting rid of all potential and kinetic energy terms out of the first law of thermo. We're going to have an adiabatic pipe. So we're not losing any heat to the environment. We're not gaining any heat. We're not generating any heat. Um, when I said steady state, that applies only to the flow. We know the temperature is not steady state. We know there is some energy stored in this fluid because they're asking us for the temperature rise. Constant material properties and no heat generation within the fluid, where it's not combusting, it's not doing anything crazy. So first we want to ask ourselves, is the flow laminar? That's a Reynolds number question. Remember, the critical Reynolds number for pipe flow is 2300. We've got, if we take our fluid flow velocity and set it equal to some, basically this is just saying, okay, we've got a set amount of mass flowing down this pipeline with a certain amount of a certain density that gives us a volume. If we divide it by the area, that'll give us, that'll take volumetric flow rate divided by area, and that'll get us velocity, fluid velocity. This should actually say meters per second, but it's about half a meter per second, so it's not particularly fast. So then we've got our Reynolds number, rho mu or rho u d over mu, which you can also do it as u d over nu, but that's a different one. It's the same thing. I just prefer that version. So if we do it that way, we get a Reynolds number of about 700, which is definitely less than 2300, which is probably laminar flow. We can calculate our Moody friction factor from this because it is laminar. It's 64 divided by the Reynolds number with a characteristic length of a diameter, which is what we did for the Reynolds number. And we get a Darcy friction factor of about 0.09. If you actually look at the friction factor chart, that's like right at the edge of where it turns laminar, but like we'll accept it. This is a pressure drop equation out of your textbook. We've got our delta P is equal to the friction factor times the density times the velocity squared divided by twice the diameter times the distance traveled. And we've also got our pump or fan power required to keep that up. And that's going to be our pressure drop times our volumetric flow rate. What we can do is if we calculate that pressure drop, that's actually not very much. We've got our kilograms per meter cubed, meters per second squared, so that's actually meters squared per second squared. Meters, these cancel. Couple of meters, these are the meters, and the cubed meters cancel. And we end up with kilograms per meter second squared, which is pascals. We double sanity check that over here. So our pressure drop is only about 8 pascals. I should mention the reason that we are doing this actually is to figure out, because typically all of this, the flow work and the pressure drop and the temperature rise are assumed to be negligible for incompressible flows, steady incompressible flows. And we would just like to corroborate that, right? And if we drop over here, we can calculate that actual the pump power, or in this case it's a pump, it's a liquid pump power as our pressure drop, which is kilogram meters per second squared. There's kilograms per meter second squared. times our mass flow rate divided by our mass density. Some stuff cancels out. We get kilogram meters squared per seconds cubed, and that actually is watts if we sanity check ourselves here. So we're only consuming about 5 watts as required to keep this going over 100 kilometers, which is actually pretty small, honestly. That's tiny. Um, and then if we do first law of thermodynamics, just to see if we can quantify that heat, we know that it's adiabatic. So this Q term actually is not the heat change within the system. It's the heat change either from the system to the outside or vice versa. We assume it's an adiabatic insulated pipe, so we're getting rid of that. It's steady flow that has no change in velocity or elevation. So we have no kinetic or potential energy terms. Our pressure drop is pretty minimal. So because we're assuming a small pressure drop and we're also assuming in this case a small temperature drop, I'm just going to say we've got a negligible enthalpy change because there's also no like phase change. So the enthalpy change should be pretty minor. And since it's one inlet, one outlet, our mass enthalpy terms should go away. They should cancel each other out, which leaves us with the change in energy, because remember, not steady state this time, in terms of temperature, is equal to our negative flow work. And our change in energy is just going to be m dot Cp change in temperature. And if we do that, if we say, okay, we've got, we're putting in 4.62 watts, and we're going to say m dot Cp delta T. Our kilograms cancel out here. Our kelvins cancel out here. Get joules per second, which is watts, and we get and then those. Sorry, the temperature doesn't cancel because there's no temperature here. Apologies. Let's redo the units. Our kilograms cancel. Joules per second is a watt, so our watts cancel. We're left with delta T is in Kelvin, which is the same as degrees Celsius when it's a delta. And what we end up with is our delta T is like smaller than millikelvins. It's tiny. So we can safely confirm that the pressure drop, flow work, and temperature rise in steady, incompressible flows is negligible. Thank you.